you hear me now? Oh, yeah, that works. Okay, everybody, hello. And we're back. So I started talking about density last time. And I'm just going to do a couple of examples of center of mass and centroid. Actually, probably just one example of center of mass and centroid, because I just want to do one example. So I recall to you that the definition of the x component of the centroid is equal to the triple integral over the domain of x dv divided by the triple integral over the domain of dv. That's the x component of the centroid. The y component of the centroid, you replace this with y. The z component of the centroid, you replace that with z. Regarding the center of mass, I gave the notion of density last time, how we computed density, or how we think about density. Oh my goodness, this is going to be problematic. And so the x component of the center of mass, m, is going to be the triple integral over the domain, d, of x times the density, which is going to be a function of x, y, and z, times dv. Notice that this numerator has units length times mass per volume times volume. So that's length times mass. And you would divide it by the triple integral over the domain of the density x as a function of x, y, z, dv. Where this is mass per unit volume times volume. This is the mass-weighted center of an object. Okay? So when you've seen centroid and then you've seen center of mass, you can now have a notion of center of any quantity you want. Charge center is another one that we would do. Okay? The center of charge. Of course, that's just the x component. The y component and the z component are just simply you replace x by y, x by z over here. Okay? So I was just thinking of I'm going to give you one more example about this. And then I'm going to talk for a moment about a moment of inertia. And then we're going to move to cylindrical and spherical coordinates. So what's an example I want to do? I was just thinking about a fun example. And I think I'm going to go a ship, e.g. a ship. Okay? I like the ship example. I'm going to do a very easy density, however. Maybe I won't do too easy of a density. I'll do a hard density. Hard. As hard as you would get on a quiz. Okay. So let's do a hard density here. So my ship is going to look, this is going to be a mathematician's ship. So here's I'm going to draw the ship as follows. This is going to be my x-axis. This is going to be my z-axis. My y-axis is going to be into the board. And my ship is going to be a piece of paper kind of folded like that. It's going to be a triangular ship, okay? Just because I don't want to worry about the details of this ship. So this is looking down the length of the ship. It's going to be like a triangular box. Okay, so maybe it's going to look like that. Whoever's homework this is, I apologize. It's going to look like that. Okay? So it doesn't have good hydrodynamics, right? It's got a flat face. Okay, it's going to have a flat face. So let's give some parameters here. Maybe we'll just call this, from this point to this point, the height of the ship is going to be h. So that's going to be h. And this will be 0, h is going to be that point right up here, okay? Because we'll do this with coordinates. This is going to be the origin 0, 0. And we'll make the width of the top be equal to w, maybe, the width of the top. Okay, so this is going to be the point w over 2. And so this is the point on the x-axis, w over 2, and this is going to be negative w over 2. Okay? And I'm going to make this, if I were to turn this ship, I'll make the ship be of length L. Okay? Now, if I'm going to put my y-axis here, where should I put the ship? So it's going to go into the y direction, right? That's the y direction is the direction of travel, so that's the direction it's pointing. Where should I put my y-axis? Anybody want to suggest where I put the y-axis? If the ship has a length which is L, where should I make y equals 0 be? Which is where? L over 2. Why would you do that? So the hope is that if you center this properly, the computation for the y component of the centroid will be 0. In fact, I've centered it properly on x, like you pointed out. And ideally, the x component of the centroid will be 0, according to this calculation. OK? Is that good? So I think what we'll do is say the ship, so this is the domain, and the ship goes from negative L over 2 less than or equal to y, which is less than or equal to L over 2. So that specifies the domain, this kind of triangular prism. Okay? Now, I'm going to calculate the centroid, and I need to calculate the center of mass. So I need a density, which is a function of x, y, and z. Okay? I need a density, which is a function of x, y, and z. And maybe we'll use my favorite kind of simple function. Let's choose a linear function. Okay? Let's choose a linear function density. So real ships. How are real ships laden, right? The real ships are laden with containers on the top and stuff in the bottom. I don't know what they put in the bottom in these big container ships. Or you have oil, an oil tanker. Let's consider an oil tanker. The truth of the matter is, if you put any fluid in the hull of a ship, that thing has constant density, right? It's a constant density thing. Oil, the density of oil at the top of the oil and the density of oil at the bottom, in a tank is not significantly different because you can't really compress oil. You can't squeeze it to create more density. So a constant density situation is actually pretty realistic, okay? But maybe we can do a linear density situation instead, okay? So let's choose a linear density here, and I'm going to choose a linearly decaying density just because it's something different. And so let me say it's going to be independent of x and y. It's just going to be larger at the bottom and smaller at the top. Okay? So what I need is a parameter, so maybe I can say down here it's some constant delta 0. Okay? And then it's going to decrease as you go up. Okay? So it's going to decrease. Sorry, that's going to equal delta 0. I just want to give myself more space. And I wanted to achieve a value of delta 1 at the top. So I'm going to or delta h. So I'll call this delta h. And that's going to be delta h minus delta 0 over h times z. So if you see this function, this is a basic linear function, which at z equals 0 is equal to delta 0. And z equals h is equal to h divided by h is 1. Delta h minus delta 0 plus delta 0 is delta h. Okay? So you've just constructed a linear function, or we have together. Now, so first, let's calculate the denominators first. Let's calculate the denominators, okay? So the denominator of the first thing I need to calculate is the volume of this ship. The volume. Okay? So the volume is equal to the triple integral over the domain of dv. That's all it is. The triple integral over the domain of dv. Well, I am actually going to do the y integration first. And y is going to go from negative L over 2 to L over 2, and I'll do that dy. And then which integration should I do next? I think I will do the x integration next. Okay? I'm going to do the x integration next. So the x integration, and then the z integration. Okay? So if you take a look now, to do the x integration, I have to have the equation for this line and this line. Well, this is the line that goes through this line over here is the line that goes through W over 2 and H, that point W over 2 comma H, and it goes through the origin. So if you were to write the equation for this line right here, you should probably convince yourself that this is Z is equal to H times X divided by W over 2. Okay? Convince yourself this is a y equals mx plus b type situation. Z equals mx plus b. But b is the intercept. The intercept is 0. M is the slope, is the rise over the run. Well, the rise is h, and the run is w over 2. So I just wrote it like that. Okay? And you can see that when x is w over 2, that cancels this, and z is equal to h. When x is 0, z is 0. Okay? So this is z equals 2hx divided by w. Okay? That is the equation for this line. And I hope it's not so hard to convince yourself, that's that curve over there, to convince yourself that this one is z equals negative 2hx over w. Okay? So that's how I have z in terms of x. But I've chosen to do my integration. I need x in terms of z. Okay? And x in terms of z is just to invert these functions. X leftmost is going to be the solution of this equation, which is negative wz over 2h. That's this, just solving for x. And of course, the positive one is wz over 2h. And with sincerest apologies, I'm writing smaller than I should have. Okay? So that's going, at constant z, you're going across this direction. And now you have to integrate vertically from z equals 0 to the uppermost value, which is pretty clearly equal to h. So that's the integral I have to do for volume. Now, the thing with these problems is once you've set them up, you can do all the other computations because you really want to set them up once and for all. Get that domain set up once and for all, okay? That's what you're doing, setting it up once and for all. So whatever order you use, you hope that you can use the same order over and over again. Okay, skipping steps. This is L, okay? This is wz over 2h. So the x integral is going to be this minus this, which is wz over 2h minus wz over 2h, which is wz over h. Okay? So this is equal to the integral of wz over h with respect to z from z equals 0 to z equals h. Now, you're going to be like, what? You're just going to find the area of the triangle times the length, right? I mean, pretty obvious. But nonetheless, I'm using this as an opportunity to talk about bounds of integration. This is z squared over 2, so this is going to be h squared over 2, which is lw h over 2, which is the area of the triangle, height times width over 2, multiplied by the length. Now, let's do the second calculation. The second computation is the mass. The mass, so I want to, let's do the second computation, which is the mass. So how do I calculate the mass? Well, the mass is equal to the triple integral over the domain D of the density integrated with respect to volume. And if I've done this nicely, I hope that I can continue to use this order of integration. So I'm going to do y x z again. So the z integral is going to go from 0 to h. The x integral is going to go from negative wz over 2h to wz over 2h. And then the y integral goes from negative L over 2 to L over 2. And now I need my delta. And that's my delta over there. Delta is delta 0 plus delta h minus delta 0 over h times z. I integrate that dy. I integrate that dx. I integrate that dz. Okay? Now, the y integral, again, is trivial. in the sense that it just comes out to L. Oh my goodness. Okay, so the y integral comes out to L. The x integral comes out to x, which is evaluated at the top and the bottom again. So that's going to give me a w over h times z, which I have to keep inside the integration. The z integral is the integral from 0 to h. This z came from the x integration. And I got z times delta 0 plus delta h minus delta 0 over h times z. And I integrate that with respect to z. Okay? This z came from the wz over 2h. And I just pulled the w over h out front. Okay? And now we have length times width divided by height. This is going to be equal to z. When I do the integral, it's going to be z squared over 2 evaluated at h and 0. That's h squared delta 0 over 2 plus delta h minus delta 0 over h. This is going to be z squared integrated, which is z cubed, which will give me h cubed over 3. And you've seen things like this before. And let's watch how all the units work themselves out. I'm going to factor out an h squared out front, and an h squared will cancel an h. So this will be LW L times W times h, length times width, and then I factor the h squared. It's going to cancel 1 power of h. And then I'm going to have a delta 0 over 2 from here, plus delta h minus delta 0 over 3. Okay, I think you might have seen something like that before. Why? Well, this is h cubed divided by h is an h squared, which is common to both, comes out, cancels an h. There you go. And if I were to just finish this up, this is LW. I would write this like this. L times W times H over 2. That's the way I would write it. Okay? And then I'm going to factor out a factor of 2. I'm going to have delta 0 minus 2/3 delta 0, which is a third of delta 0, right? And so this should be delta 0 plus delta H over 3. I think that's what I got. So I factored out the 2. I factored out this 2, LWH over 2. That means I've got a 2/3 over here. Oopsie. Sorry. Delta 0 plus 2 delta H over 3. I forgot that too. Okay? You guys okay with that? Okay, so why did I factor it out? Well, the first thing is, this is the volume of that shape. This is the total volume of the shape. Okay? Together, this forms the mass of the shape. Right? This is the mass. This is a density, right? This has to be density because it's density plus density times volume. Okay? And so what I've calculated is the total mass of the shape, and I've extracted the total volume of the shape. I can now actually tell you what the average density is. Right? Because the average density would be the total mass, which is that thing, divided by the total volume, which is the thing that I put out front. So this is the average density. So when you have a linear function of height in this way, the average density is apparently the density at the base plus twice the density at the top divided by 3. Okay? And you can think of, oh, wow, it's interesting that the coefficients here add up to 3, and you're dividing by 3 in the end. And you could ask the question, what if I had a quadratic profile or different profiles of density? What would it look like? So this is, in fact, the total mass. But because this is the volume, this is the average density, the stuff in parentheses. OK. That's, I think, interesting. I think it's kind of interesting. Well, how would I get the centroid here? Do people want me to do the computation of the centroid? Am I losing you guys? It's too boring? It's too easy? OK. What part? OK, so if I'm losing you, it's incumbent upon you to slow me down and ask me a question. I'm sorry. But I need your help.
I just, the skipping steps sometimes trips me up a little bit.
Okay. So what you should, so yes, skipping steps will trip you up, right? But that's not my responsibility not to trip you up. So why won't you, it's okay, you're tripped up. The question is, do you focus on the trees or do you focus on the forest, right? So I skipped the steps so I can get to the forest, so I can show you this beautiful forest over there, right? And you can write, what you want in there, and then one of the things you should do if you're a little tripped up is to go fill in the details, right? Because the integration was trivial. I mean, I'm just integrating z or z squared or z cubed. I mean, I'm not doing crazy functions over here, right? I really want you to see the setup, okay? So if the setup is tripping you up, that's important. If the computation is like, okay, I didn't see how he skipped that step, then I want you to say, okay, I will go and work that out, okay? Yeah, I know. It's tough to say, do you follow the computation or do you follow the bigger picture? And I'd like you to stay with me with the bigger picture, okay? So I hope this didn't trip you up and this didn't trip you up. And well, maybe some of the simplifications didn't trip you up, but now that I've got this at the end, volume times density is mass, that shouldn't trip you up. And then you say, okay, let me see what it means. How do I interpret it, okay? And then you can go back and fill in the details. Because I promise you I'm not going to do super hard integrals right here. Yes, sir?
Is the density just an arbitrary formula?
I gave you the density. It has to be given to you. So there is a shape and there's a density. Okay? There's a shape and there's a density. The way I said it last time is, my eye sees you and identifies your centroid. We can do that computation pretty straightforwardly. Because we see the shape of the person or the object. Right? Identifying the center of mass is a different kind of thing. Right? Identifying the center of mass is not as easy because where the mass is in that object is not obvious. Right? The ship is a perfect example because there's a heck of a lot of mass at the bottom because the density is really high at the bottom and much less mass at the top. Okay? It's been laden down with something heavier at the bottom. And I gave you this arbitrary density profile. So it's additional information. Okay? This is good? So where would the centroid be? Let's do the centroid really quickly. So I've calculated the denominators right now. The x component of the centroid is 0. The y component of the centroid is 0. We kind of agree with that. The x component of the center of mass is 0. The y component of the center of mass is 0. Because all of that symmetry should make things be 0. Now it's the z components, right? It's the z components we need. So let me get, what I need to calculate is z times the volume. So the numerator for the center of mass, the centroid. So this is part 3. Numerator for centroid. Okay? So what's the numerator in the calculation of the centroid? Well, we want z. It's going to be the triple integral over the domain of z dv. Okay? And it's the same setup as we had before. So I'm going to be going fast, 5th gear, right? So those of you who are having problems keeping up with me, just look at the forest, right? Just say, okay, that was all super plausible or not. But don't worry about the details of this calculation if you're losing, if you think I'm going a little fast. So it's going to be 0 to h, negative wz over h to wz over h, from negative L over 2 to L over 2, z dy dx dz. The y part of it, again, just pops out an L. That's why I made it so simple there. So I'm not really doing a triple integral. The x part just pops out an x, evaluate the upper and the lower bound. So that's going to be the integral from 0 to h of this z multiplied by this minus this. And there was a 2 there. Apologies. So that's wz over h. And then I have to integrate that with respect to z. Yes, did I make a mistake?
No, I have questions like, let's find the density of the ship.
No. So, okay, again. You're an engineer. Here's a ship. Here's the shape of the ship. I'm giving you also iron ore or something to put in that ship. Okay? So I'm telling you, the problem tells you the shape of the ship and the density. The density is delta. The shape is that shape with those boundaries. I am using that information. Okay. To find centroid, all I need to know is the shape of the ship. I need to know the boundaries of integration. To find center of mass, I need more information. I need to know where the mass is. So to find center of mass, I need shape and density. Okay? So I'm giving you shape and density. And we're doing two numerators, which are those, that's one of the numerators. The other one will have the density in there. And then two denominators. One will be the mass and the other one is the volume. Okay? Okay. The integral, this is a w, which is the width. This is an h, which is the height. I've got L times W divided by H. I'm just pulling them out. The integral of z squared is z cubed over 3, which evaluate the upper bound is h cubed over 3. So this is h cubed over 3. Which if you write it out is L times W times H. I got another H. I got a factor of 3. And now, if you don't mind, I'm going to divide this by 2 and multiply by 2. It's just another way to look at the same constants, right? I didn't have to do that. But let me show you why I did that. This is the volume of the ship. And what I said is z bar, the centroid, is this thing divided by the volume of the ship. So z bar, the centroid, I'll write it up here, z bar, the value of the centroid, is that integral divided by the volume, which is equal to 2h over 3. Okay? So the reason I put the 2 here was to get the 2 back up. Well, the reason I put the 2 here was to get the volume. And therefore, I had to put the 2 back up there in order to not change the problem. I could have written it as LWH squared over 3. But this is more illuminating. So if you collect terms properly, it can make the answer more illuminating. And I've said that before, too. Okay? So this tells me that the centroid of this triangle, or the centroid of the ship, is along this axis. And if along the length of it, it's along the, it's at y equals 0 if it goes from negative L over 2 to L over 2. And it's at a height. So the centroid is at a height here. Something like that. If this is h, this is 2/3 of h. Which is plausible, right? It's plausible. It's 2/3 of the way up. We okay with that? Now let's find the center of mass. If delta 0 is bigger than delta h, where do you expect the center of mass to be? Above or below the centroid? Below. If it's heavier at the bottom than it is at the top, you expect the center of mass to be below the centroid. So let's do the center of mass computation. Okay? The numerator for the center of mass, I'm going to leave that because that was our, well, I have that written over there. Z bar is 2/3. Okay? The numerator for the center of mass is what? Well, it's z times the density as a function of x, y, and z times the volume. No worries. That was not your fault. Is it important?
This is a test of the commercial mobile alert system. This is only a test.
Not important. It's okay. I don't care if the alert systems go off. I want to know. It doesn't matter. If I need to know if there's a reason for an alert. That is not a biggie. Okay, so guys, length times mass. Length times mass, right? Length, mass per unit volume times volume is length times mass. What did I do wrong? Because because the x component of the centroid is the triple integral of x dv divided by dv. The y component is the triple integral of y dv divided by dv. The z component is the triple integral of z dv divided by dv. And the center of mass, the center of mass is the same thing, except it's x times the density dv. So I'm doing this numerator, except for the z component of the center of mass.
X and Y are the centroid of X and Y are 0.
Yes. I thought we established that. You and me talked about that a few minutes ago. Yes, thank you. Yes, because the x and y component of the center of mass and because the x and y component of the centroid are 0, I'm not going to bother computing them. That's why I centered the whole thing, so I don't have to do tons of integrals. Right? I'm doing enough now that I'm barely keeping you guys awake. So if I do some more, it's going to be a disaster, right? So we've chosen to position the ship in such a way that we found the x-axis of symmetry and the y-axis of symmetry. It's just that this z thing can change, right? Because it's a triangle. So the centroid is 2/3 of the way up. And now where's the center of mass? I really want to know. I'm dying here. I'm sure you guys are just at the edge of your seats. Well, so the answer is going to be yes. And let's prove that too. I can actually show you that that's going to be true in a second, okay? Because I've done this general enough. So now think about this. You have a density that's d0 here and dh up there. I haven't actually said that dh or I haven't said which one is bigger yet. I haven't told you which one's bigger. But I'm just, I mean, you usually think the density at the bottom is a little bigger, right? But it doesn't have to be. Let's see where this center of mass goes, okay? So I've got this formula over here, which is the total mass. This is the numerator for the center of mass, the z component at least. So I need to do this, right? So again, same setup, 0 to h, negative wz over 2h, positive wz over 2h. And then I have to go from y equals negative L over 2 to y equals L over 2. Now I got a function here, so I got to breathe. Let's do this. We got z. That's the z function that it gives me the distances of the points from the plane, the z equals 0 plane. Then delta is delta 0 plus delta h minus delta 0. That's the linear function divided by h times z. So it's a more complicated integral, but it's only a linear function. I know a lot of people don't like having these variables here. You can put a 5 and a 3 and a 2. Sure. But it's much more interesting to see how the answers change if you change these underlying parameters of the problem. That's really what you want to do with these computations. So there's the dy, then the dx, and then the dz. Okay? Again, the dy part of it gives me L. Okay? The dx part of it gives me just this multiplied by that. So I'm going to have the w over h, which has been ubiquitously coming out of that integral. Because of this, it's coming out again. And then I have to do the integral from 0 to h of this z, which is still sitting there, this z, which is still sitting there, delta 0, which is always going to sit there, delta h minus delta 0 over h times z, and then I integrate that with respect to z. That's the integral I have to perform for the numerator. Now, I don't want to lose this. These are easy integrals to do. I've chosen linear functions. This is the integral of z. The first term is the integral of z squared, which is z cubed over 3. Okay? So I have LW over h times delta 0. And this is going to be z cubed over 3, evaluated at h and 0. So that's just h cubed over 3. And then this one is the integral of z cubed, which is going to be z to the 4th over 4. So this is going to be delta 0 minus delta h over h times h to the 4th over 4. Okay? Now, I didn't promise you a rose garden here. I didn't say this was going to be beautiful and simple and trivial, right? There's something to it over here, okay? It's a little bit of a back and forth. You got to be a little careful, but it'll work out nicely in a moment. So notice there's an h cubed common to the whole thing. This is a 1/3 and this is a 1/4. This is going to be L W H cubed. LWH cubed, I'm just going to be careful because I can't do the factorization as easily this time because my brain is not that good. Sorry guys, this is delta H minus delta 0. Delta H minus delta 0, that was... Yeah. Yes, thank you. Thank you. Yeah, you guys are right. I factor out an h cubed, but I must divide said h cubed by h. So this is h squared. Very good. Delta naught over 3 plus delta h over 4 from here minus delta h over 4. Delta 0 over 4. Now I'm starting to make algebraic errors, which you guys will not be happy about. So this is going to be LWH squared. I'll pull the 12 out front. You can see that there's a common denominator of 12. That's going to be 4 minus 3 is 1. And this is going to be 3. So this is going to be delta 0 plus 3 delta H. And if I'm lucky, this thing originally started with units length times mass per unit volume times volume. And here we have mass per unit volume times length times volume. Okay, so I've maintained my units. Now to get the z component of the center of mass, I have to take this and divide by that, because that's the total mass. So let's do that division. Okay, let's do the division. We have to be a little careful. That divided by that, I'm just going to write it out because otherwise I'll make a mess. Z component of the center mass equals the delta terms. I'm going to write them delta 0 plus 3 delta H. That's from over here. And then the other one is going to be a delta 0 plus 2 delta H. That's the one from up there. I've got an LWH squared over 12. That's from here. I've got an LWH over 6. So I'm going to write that 6 over LWH is from there. Okay? So LWH clearly cancels out of this whole problem. LWH clearly cancels out of this whole problem. And then I'm going to have a 6 over 12, which is a half. So this is going to be h over 2. You're going to get an h divided by 2 times this thing, delta 0 plus 3 delta h over delta 0 plus 2 delta h. Okay? Now, I hope I didn't make a mistake. Yeah, no, I didn't make a mistake. I did not make a mistake. I feel like I made a mistake. Did I make a mistake, anybody? That's what you got? Yes. Yeah, but it's divided by this h over here. Yeah. Dimensionally, it has to be all densities here, because you can't add density to density divided by height. So, yeah, keep that observation. Yeah, keep looking, right? It is very possible that I made a mistake. So what's a simple situation? What if delta h equals delta 0? If delta h equals delta 0, that means the density should be constant. That means the center of mass should be where the centroid is. Okay? Now, that's why I was wondering if I made a mistake. if delta H equals delta 0, delta H equals delta 0, okay? If delta H equals delta 0, then then Z bar C is equal to H over 2. And you can factor out the delta 0 here, so you're going to get a 4 divided by 3. Oh, yeah. 2/3 H. Ta-da! Thank you very much. Thank you very much. Those of you who are awake. So when delta H is delta 0, we recover the answer that the center of mass is where the centroid is, right? Let's consider a different extreme. Let's consider the case delta H is 0, right? So the density goes from some bottom density to 0 at the top, right? And in that case, when delta H is 0, delta H is equal to 0, okay? What happens in that case is Z bar C, the location of the center of mass, this is Z bar M. I apologize, Z bar M. We're talking about the center of mass. Well, when delta H is 0, these guys are 0, and delta over delta is 1, so that occurs at H over 2. So if the density goes down to 0, then, if it's a constant density, the center of mass and the centroid are the same place. If the density is bigger here and goes down to 0, that pushes the center of mass down to H over 2. Intuitive, I hope? You would expect it to be lower because there's less density at the top. Okay? And what's the other extreme? What about the case of delta 0 equals 0? So now let's do the opposite extreme, right, where the density at the bottom is 0 and the density at the top is really high. I don't know, that's not a ship you want to have, right? That's kind of a dangerous ship where there's a lot of mass at the top and nothing at the bottom, okay? And, well, what do you get there? Well, this is going to be 0 and 0, and this is going to be at 3/4, right? This is 3. The delta H's are going to cancel. It doesn't matter what the delta H is. It's going to cancel. 3 over 2 over 2, so this is going to be Z bar M is at 3/4 H. So it's 3/4 of the way up. So you can see you're playing with the location of that delta, of that center of mass. And if you've ever been in a ship that's tipped, if you've ever sailed or something like that, okay, and I do, right, you need a lot of mass at the bottom. They put a keel, okay, at the bottom, like this big thing that goes down, this big heavy thing that goes down underwater to keep the ship from tipping because you want your center of mass really low, okay? And so this is the different comparisons of what center of mass and centroid give you. Now, I know I did a very general problem, but that's what I want you to see. I want you to see how you can consider families of problems, right, by having different laden ships, different shapes of ships, okay? I'm sorry if you guys got lost in some of the trees for that one. No, but you're not alone. You're not alone. I mean, I'm talking to you, but you're my channel to the classroom, right? And I appreciate you telling me that because it gives me an opportunity to have a conversation with everybody else too. Okay? So, yeah, I know people are going to get lost in some of the trees here. But I think this is a pretty little result. I think it's a pretty little result. And since I don't have a lot of time, I'm not going to introduce a new topic. I just want to tell you another way I would write this. Okay, the way I would write this as an applied mathematician, as a person who's thought about fluid dynamics for a long time, and maybe engineers do this also, you factor out the delta 0 from the numerator and denominator. And you realize that this is H over 2 times 1 plus 3 times the density at the top divided by the density at the bottom. This ratio, it only cares about the ratio of the density at the top to the density at the bottom divided by 1 plus 2 times the ratio of the density at the top to the density at the bottom. That's another way that people will look at these things. And this is called a non-dimensional ratio. And we do a lot of those things because we want to know how it scales. Right? We didn't actually care that the density at the bottom was 10 grams per cubic centimeter and the density at the top was 1 gram per cubic centimeter. We cared that the ratio was 1 divided by 10. So you could have done this for rocks and iron ore, or you could have done it for marshmallows and, down feathers or something like that. It's the ratio that matters. Okay? That'll come up a lot in your physical problems and your engineering problems. And it comes up a lot in mathematics. So for the first time in my life, I'm actually going to stop a class a little early, unless I have any questions. Or let me stop the class early and then say, if you want to ask me a couple questions, come sit in the front row and I'll do a math problem for you if you want. But you guys, that's all I'm really going to talk about today. Yeah.
Essentially, email about the quiz.
You got what?
No problem. Hi there.